Notice how everything you see is revealed by photons that began their journey in a place beyond imagining a cosmic furnace where matter itself transforms, where the universe writes the story of energy into existence. Every single moment of warmth you've ever felt from sunlight, every shadow you've ever cast, every sunset that's ever taken your breath away, all of it powered by a star. Our star, a sphere of plasma and light 93 million miles away, burning with such intensity that it could incinerate anything that dared approach too closely, yet perfectly calibrated in its distance to make life not just possible. The sun is not simply a glowing ball in the sky. It is a vast nuclear reactor, a gravitational colossus, a magnetic dynamo, and the beating heart of everything we know. Every breath you take is possible because ancient cyanobacteria learned to harvest this star's light. Every bite of food you eat contains energy that flowed from the sun through the patient architecture of photosynthesis. The very atoms that make up your body were forged in stellar furnaces, much like our sun, scattered across space when those ancient stars died and gathered again into the rocky world beneath your feet. Right now, as you listen to these words, the sun is converting 620 million metric tons of hydrogen into helium every single second. 620 million tons each second. The scale is almost impossible to grasp. In that process, 4 million metric tons of matter simply cease to exist. As matter, they transform into pure energy, according to Einstein's famous equation. That missing mass becomes the light warming your face, the energy that drives Earth's weather, the power behind every living thing that has ever existed on this planet. And it has been doing this with remarkable stability for 4.6 billion years, long before the first human looked up at the sky in wonder, long before the dinosaurs walked the Earth, long before Earth itself had cooled enough to have oceans. The sun was already middle-aged when our planet formed from the debris disk swirling around it, and it will continue burning for billions of years after the last trace of human civilization has vanished. Tonight, we're going on a journey into this cosmic engine. We'll descend into its core, where reality itself is being rewritten at temperatures beyond human comprehension. We'll trace the patient journey of light through layers of plasma so dense that a single photon takes nearly 200,000 years to escape. We'll ride the solar wind out into space and watch as it shapes the magnetic environment of our entire solar system. And we'll look forward into deep time to witness the sun's eventual transformation into something entirely different. A transformation that will fundamentally reshape or destroy everything we know. This is a story about the most important relationship in your life, even if you've never thought of it that way. It's the story of our sun, and of the narrow window of cosmic time in which we find ourselves alive beneath its light. Number. 4.6 billion years ago, in a quieter arm of the Milky Way galaxy, something was stirring. A vast cloud of molecular gas and dust, mostly hydrogen with a mixture of helium and trace heavier elements, was drifting through space. This nebula was enormous, perhaps dozens of light years across, and it had been floating peacefully through the void for who knows how long. But then something happened. Maybe a nearby star exploded in a supernova, sending shock waves rippling through space. Whatever the trigger, a portion of this cloud began to collapse. Gravity is patient but relentless. As the cloud contracted, it pulled itself inward with increasing force. The collapse wasn't uniform. The cloud fragmented, forming knots of denser material. One of these knots, relatively unremarkable in the cosmic scheme of things, continued to shrink. As it did, it began to spin faster, like a figure skater pulling in their arms. The conservation of angular momentum ensured that this collapsing ball of gas began to rotate, and the rotation flattened it into a disk with a growing, dense bulge at the center. The center of this bulge was getting hot. When you compress gas, it heats up. This is basic physics. the same reason a bicycle pump gets warm when you use it. But the pressures building at the heart of this collapsing cloud were far beyond anything you could create with a pump. As more and more material fell inward, drawn by the growing gravitational pull, the temperature at the core climbed. 1,000,000 degrees Celsius, 5 million, 10 million. The pressure became so intense that it would be measured not in atmospheres, but in billions of atmospheres. And then, when the core reached approximately 15 million degrees Celsius, something remarkable happened. Hydrogen nuclei protons, each carrying a positive electrical charge, were moving so fast and colliding so violently that occasionally, against all odds, two of them would overcome their natural electromagnetic repulsion and fuse together. In that instant of fusion, one of the protons transformed into a neutron through the weak nuclear force, creating a deuterium nucleus and releasing a positron and a neutrino. The deuterium nucleus would then capture another proton, forming helium-3. Two helium-3 nuclei would eventually collide and fuse, creating helium-4 and releasing two protons back into the mix. The net result of this process, called the proton-proton chain, was that 4 hydrogen nuclei were transformed into one helium nucleus, with a tiny amount of mass converted into energy. And when I say a tiny amount, I mean tiny in proportion to the original mass, about 0.7%. But that tiny fraction, when released from 620 million tons of hydrogen every second, produces an almost incomprehensible amount of energy. 3.8 times 10 to the 26th watts. That's a 3 followed by 8, followed by 25 more zeros, measured in joules of energy released every single second. The protostar that would become our sun had ignited. The outward pressure from this nuclear fusion balanced the inward pull of gravity, and the star stabilized. It would remain in this balanced state, this equilibrium between collapse and explosion, for about 10 billion years. We call this phase the main sequence, and it is by far the longest and most stable period in a star's life. Our sun entered its main sequence about 4.6 billion years ago, which means it's roughly halfway through this stable burning phase. Think about what this means. When the first single-celled organisms appeared on Earth, about 3.5 billion years ago, the sun was already more than 1 billion years old, already settled into its steady rhythm of fusion. When those cells learned to photosynthesize, harvesting the sun's light to build complex molecules from simple ingredients, the sun was exactly as it is now, a stable, middle-aged star. When the first animals crawled onto land 400 million years ago, the sun had already been burning for more than 4 billion years. When your ancestors first looked up at the night sky and wondered about the lights they saw, they were seeing the same star that had witnessed every moment of Earth's history. The sun formed alongside the rest of our solar system. As the central protostar grew, the disk of material swirling around it began to coalesce into larger and larger chunks. These would become the planets, moons, asteroids, and comets that make up our cosmic neighborhood. The inner regions of the disk, close to the young sun, were too hot for light elements and compounds to condense. Only materials with high melting points, metals, and rocky minerals could remain solid. This is why the inner planets, including Earth, are made of rock and metal. Further out, beyond what we call the frost line, it was cold enough for water, methane, and ammonia to freeze into ice. Here, the forming planets could grow much larger, accumulating thick atmospheres of hydrogen and helium. These became the gas giants: Jupiter, Saturn, Uranus, and Neptune. But all of it, every planet, every grain of dust, every molecule in your body is made of material from that original nebula. The iron in your blood, the calcium in your bones, the carbon in your DNA, all of it was floating in that cloud 4.6 billion years ago. And much of that material was itself the remnant of even older stars that had lived and died before our sun was born. You are made of stardust in the most literal sense. Your atoms have cycled through multiple generations of stars, each one fusing lighter elements into heavier ones, each one scattering its enriched material back into space when it died. The sun you see today is the same star that formed all those billions of years ago, but it's not exactly the same. Stars evolve slowly, gradually changing their properties as they age. When the sun first settled onto the main sequence, it radiated only about 70% of its current luminosity. Over the 4.6 billion years since, it has steadily brightened, and it will continue to do so. In another billion years, it will be about 10% brighter than it is now. This gradual brightening has profound implications for Earth's habitability, as we'll explore later. For now, let's appreciate the sheer stability of what's happening. The sun has been burning hydrogen into helium at a nearly constant rate for billions of years. This constancy is not guaranteed. It emerges from a delicate balance between gravity, trying to compress the star, and the pressure from fusion, trying to expand it. If fusion slows down for any reason, gravity compresses the core, which heats it up, which speeds up fusion. If fusion gets too vigorous, the core expands and cools slightly, which slows down fusion. It's a self-regulating system, a cosmic thermostat that has kept our star remarkably steady for eons. This stability is a gift we rarely think about, but it's worth pausing to consider how rare and precious it might be. The universe is full of variable stars, stars whose brightness fluctuates significantly over time. Some stars flare unpredictably, others pulsate like cosmic hearts, swelling and shrinking on regular cycles. Binary stars can eclipse each other or exchange mass in violent bursts. We live in a single star system orbiting a spectacularly ordinary star, and that ordinariness is exactly what makes life possible. The sun is not too massive, not too hot, not too variable. It's just right. And it has been just right for billions of years. Number, the cosmic furnace. Let's descend now into the heart of the sun, to witness the cosmic alchemy that powers everything we know. If we could somehow protect ourselves from the heat and pressure and travel inward from the surface, we would pass through increasingly extreme conditions. But the real action, the place where the sun's energy is actually created, is buried deep in the core. The core extends from the center of the sun outward to about a quarter of the solar radius, roughly 175,000 kilometers from the center. This represents only about 2% of the sun's volume, but it contains approximately half of the sun's total mass. The material here is compressed to densities about 10 times that of lead. The core is so dense that a cubic centimeter of core material would weigh more than 150 grams. And the temperature is approximately 15 million degrees Celsius. At these temperatures and pressures, matter exists in a state unlike anything we experience in daily life. The sun is made almost entirely of plasma, which is sometimes called the fourth state of matter. In a plasma, atoms are so hot that electrons are stripped completely away from their nuclei. Instead of atoms, you have a seething soup of naked nuclei and free electrons, all moving at tremendous speeds. The hydrogen nuclei single protons are zipping around at velocities measured in hundreds of kilometers per second. Picture this environment for a moment. The core of the sun is a maelstrom of activity, with particles colliding billions of times per second. The density is so extreme that despite the incredible speeds, particles can travel only tiny distances before hitting something else. It's crowded beyond imagination, hot beyond comprehension, under pressure that would instantly vaporize any material we could conceive of bringing near it. And yet, within this chaos, there's an order. The same fundamental forces that govern interactions between particles in a laboratory on Earth operate here. The laws of quantum mechanics, thermodynamics, and nuclear physics all apply. We can understand what's happening in the sun's core because the same rules that govern the smallest scales of reality apply equally at the heart of a star. Under normal circumstances, two protons cannot get close to each other. They're both positively charged, and like charges repel. The electromagnetic force pushing them apart is strong, and it grows stronger as they get closer together. You would need enormous energy to force two protons close enough to touch. But in the core of the sun, the protons are moving so fast, and there are so many of them in such a confined space, that collisions are inevitable. Most of these collisions simply result in the protons bouncing off each other. But occasionally, very occasionally, something remarkable happens. When two protons collide with sufficient energy, quantum mechanics allows them to tunnel through the electromagnetic barrier that should keep them apart. This is one of the strange predictions of quantum physics that has been verified countless times. There's a small but non-zero probability that two protons can suddenly find themselves close enough that the strong nuclear force, which operates only at extremely short ranges, can grab them and bind them together. But two protons cannot remain bound. That would be a form of helium-2, which is unstable. Instead, one of the protons immediately transforms into a neutron through the weak nuclear force, emitting a positron and a neutrino in the process. The result is deuterium, a hydrogen nucleus with one proton and one neutron. This step, the fusion of two protons into deuterium, is actually the slowest and most difficult step in the entire process. It's so unlikely for any given collision that a typical proton in the sun's core will bounce around for billions of years before successfully fusing with another proton. This is actually fortunate because it means the sun burns its fuel slowly and steadily rather than all at once. Once deuterium forms, the rest happens relatively quickly. The deuterium nucleus doesn't wait long before it collides with another proton. When it does, they fuse to form helium-3, a helium nucleus with two protons but only one neutron. This fusion releases a gamma-ray photon, a particle of pure electromagnetic energy. Finally, two helium-3 nuclei collide and fuse, creating a stable helium-4 nucleus, two protons and two neutrons bound together, and releasing two protons back into the mix to start the cycle again. The net effect of this entire chain of reactions, called the proton-proton chain, is that four hydrogen nuclei are converted into one helium nucleus. The helium nucleus weighs slightly less than the four hydrogen nuclei that went into making it. Specifically, about 0.7% of the mass has vanished. Where did it go? It became energy, exactly as Einstein's famous equation predicts. E equals mc squared. Energy equals mass times the speed of light squared. The speed of light is a very large number, and when you square it, you get an enormous number. So even a tiny amount of mass, when converted to energy, yields a staggering amount of energy. How staggering? Well, the sun converts about 4.26 million metric tons of matter into pure energy every single second. To put this in perspective, that's roughly the mass of 4,000 blue whales disappearing and becoming light and heat every second. And the sun has been doing this for 4.6 billion years. It has converted an amount of mass equal to about the mass of Saturn into energy over its lifetime so far. Yet the sun is so massive that this represents only a tiny fraction of its total mass. It has barely noticed the loss. The energy released in each fusion reaction emerges as high-energy gamma-ray photons and as the kinetic energy of the particles involved. These gamma rays, if they could travel freely, would reach the surface of the sun in just over 2 seconds. Light travels fast, after all, but they cannot travel freely. The core of the sun is so dense that a photon can travel only a few millimeters before it collides with an electron or a nucleus. When it collides, it is absorbed, and the particle that absorbed it becomes more energetic. That particle then emits a new photon, usually at a slightly lower energy, in a random direction. This process repeats over and over and over again. A single photon created in the core will be absorbed and re-emitted countless times, each time changing direction randomly, each time potentially losing a bit of energy and shifting toward longer wavelengths. This is called a random walk, and it's extraordinarily inefficient. That photon, which could reach the surface in just over 2 seconds if it could travel in a straight line, instead takes a wandering path that lasts about 170,000 years. Think about that. The light warming your face right now began as a gamma-ray photon deep in the sun's core 170,000 years ago, long before modern humans left Africa, long before the last ice age began. The energy created in the core gradually works its way outward through this random walk process, but the journey changes as the photon moves into different regions of the sunday. Just outside the core, extending from about 25% to about 70% of the sun's radius, lies the radiative zone. Here, the plasma is still extremely dense, far denser than any gas on Earth, but not quite as dense as in the core. The temperature has also dropped, from 15 million degrees in the core to about 7 million degrees at the base of the radiative zone and about 2 million degrees at its outer edge. In the radiative zone, energy transfer happens primarily through radiation, as the name suggests. Photons continue their long random walk outward, being absorbed and re-emitted countless times. The material here is so tightly packed that convection, the process where hot material rises and cool material sinks, cannot occur. The density gradient is too steep, so the energy must slowly diffuse outward through radiation alone, a patient process that can take tens of thousands of years just to cross this zone. But as we move outward, the temperature and density continue to drop. Eventually, at about 70% of the sun's radius, conditions change enough that a different form of energy transport becomes more efficient. The material is still incredibly hot by any human standard, about 2 million degrees Celsius, but it's cool enough and diffuse enough that convection can finally occur. This is the boundary of the convective zone, and it marks a fundamental shift in how the sun moves energy from its core to space. Number, journey through the layers. The convective zone extends from about 200,000 kilometers below the visible surface, all the way to the photosphere. Here, instead of energy slowly diffusing through radiation, it's carried by the bulk motion of plasma. Hot plasma from the bottom of the convective zone, heated by radiation from below, becomes buoyant and rises upward. As it rises, it expands and cools. When it reaches the surface, it releases its energy into space as light and heat. Now cooler and denser, it sinks back down to be heated again. This is convection, the same process that makes water boil in a pot or creates thunderclouds on a summer afternoon. But the scale here is almost incomprehensible. The convective cells in the sun can be thousands of kilometers across. Imagine a rising column of plasma larger than Earth, moving at speeds of up to 1 kilometer per second, carrying heat from the depths toward the surface. The plasma is churning constantly, in a state of perpetual motion, as the sun works to shed the energy being generated in its core. When this rising plasma reaches the surface, it creates visible patterns. If you've ever seen high-resolution images of the sun, you may have noticed that the surface looks grainy or mottled, covered with bright patches separated by darker lanes. These patterns are called granulation, and each granule represents a convection cell. The bright centers are where hot plasma is rising and releasing its light. The darker edges are where cooler plasma is sinking back down. Individual granules are typically about 1,000 kilometers across, roughly the distance from New York to Florida, and they last for only about 20 minutes before dissolving and being replaced by new ones. This granulation is visible evidence of the intense activity just beneath the surface. The sun's surface is not a calm, solid boundary, but rather a seething, bubbling interface between the dense interior and the near vacuum of space. It's remarkable to realize that we can actually see this process happening. When you look at the sun through a properly filtered telescope, you're watching convection in real time, seeing plasma rise and fall in patterns that repeat constantly across the entire visible disk. The photosphere, the part of the sun we see as its surface, is actually a layer about 500 kilometers thick, where the plasma finally becomes transparent enough that light can escape into space. Below this layer, the plasma is so dense that light cannot travel far before being absorbed. Above it, the plasma is thin enough that light can travel freely. The photosphere is where the sun's energy, which began its journey in the core 170,000 years ago, finally breaks free and streams out into the solar system. The temperature of the photosphere ranges from about 4,500 to 6,000 degrees Celsius. This might seem extraordinarily hot, and it is by human standards. But compared to the millions of degrees in the interior, the photosphere is actually quite cool. This is important because temperature determines the color of light that a hot object emits. The photosphere's temperature gives the sun its familiar yellow-white color. But the photosphere is not perfectly uniform in temperature or brightness. Scattered across its surface are darker regions called sunspots. These are areas where strong magnetic fields have pushed through the surface, preventing hot plasma from rising and cooling the photosphere locally. Sunspots appear dark only in contrast to the brighter surrounding regions. They're still incredibly hot, about 3,500 to 4,000 degrees Celsius. They're just cooler than the rest of the photosphere, so they emit less light. Sunspots come and go in cycles of about 11 years. During solar maximum, the peak of this cycle, the sun can be covered with dozens of sunspot groups, some of them larger than Earth. During solar minimum, there might be days or weeks with no sunspots at all. This cycle is driven by the sun's magnetic field, which is generated by the motion of electrically charged plasma deep in the interior. The details of how this magnetic field is generated and why it follows an 11-year cycle are still not fully understood, representing one of the ongoing mysteries of solar physics. Above the photosphere, the sun's atmosphere becomes even more intriguing. Just above the visible surface lies the chromosphere, a layer about 2,000 kilometers thick. The name comes from the Greek word for color, because during a total solar eclipse, when the moon blocks the bright photosphere, the chromosphere becomes briefly visible as a thin reddish ring around the sun's edge. This red color comes from hydrogen atoms in the chromosphere, emitting light at a specific wavelength as their electrons jump between energy levels. The chromosphere is full of dynamic activity. Rising from its surface are spicules, jets of plasma, that shoot upward at speeds of about 20 kilometers per second, reaching heights of 10,000 kilometers before falling back down. There are hundreds of thousands of spicules on the sun at any given time, forming a sort of spiky layer at the top of the chromosphere. These features last only about 5 to 10 minutes each, but new ones form constantly, creating a perpetually changing forest of plasma jets. But here's where things get truly mysterious. The chromosphere is hotter than the photosphere below it. The temperature rises from about 4,000 degrees Celsius at the bottom of the chromosphere to about 25,000 degrees Celsius at the top. This seems to violate a fundamental law of physics. Heat should flow from hot to cold, not the other way around. Energy is flowing outward from the sun's core. So we would expect each layer to be cooler than the layer below it. Yet the chromosphere is heating up as we move away from the core. This temperature inversion gets even more extreme in the layer above the chromosphere. The transition region is a very thin layer, sometimes only a few tens of kilometers thick, where the temperature skyrockets from about 25,000 degrees to over 1 million degrees Celsius. And beyond that lies the corona, the sun's outer atmosphere, where temperatures reach between 1 million and 3 million degrees Celsius. The corona is visible during total solar eclipses as a beautiful, pearly white halo extending millions of kilometers into space. Its light is much fainter than the photosphere, about 1,000,000 times dimmer, which is why we can only see it when the moon blocks the bright surface. But despite being so faint, the corona is incredibly hot. In fact, it's hundreds of times hotter than the photosphere, even though it's much farther from the core where the energy is being generated. This is known as the coronal heating problem, and it's been puzzling astrophysicists for decades. How does the corona get so hot? The answer lies in magnetic fields. The sun's magnetic field is incredibly complex, with loops and arcs extending far above the surface. These magnetic fields can store energy and then release it suddenly when the field lines reconnect or undergo other changes. This energy goes into heating the plasma in the chromosphere and corona. Additionally, waves can propagate along magnetic field lines, carrying energy upward and depositing it in the upper atmosphere. The details are still being worked out, but it's clear that magnetic fields play a crucial role in explaining these unexpectedly hot outer layers. The corona is not uniform. It's structured by magnetic fields into streamers, loops, and arcs. Some regions, called coronal holes, have open magnetic field lines that extend far out into space, and from these regions, the solar wind flows freely. Other regions have closed magnetic field lines that trap plasma close to the sun, forming the bright loops and prominences that are visible in images taken at ultraviolet and X-ray wavelengths. The corona is a dynamic, ever-changing environment, shaped by the magnetic forces generated deep within the sunday. All of these layers, from the core through the radiative and convective zones, through the photosphere, chromosphere, and corona, work together as an integrated system. Energy generated in the core through nuclear fusion gradually makes its way outward, changing form and interacting with the plasma and magnetic fields along the way, until it finally escapes as the light and heat that make life on Earth possible. The sun is not just a ball of hot gas. It's a complex, layered structure, with each layer playing a specific role in the process of converting mass into energy and delivering that energy to the solar system. Number. The sun's invisible reach. But the sun's influence extends far beyond its visible surface, far beyond even the 1,000,000-kilometer extent of its corona. The sun fills the solar system with a constant stream of charged particles called the solar wind. And this invisible flow shapes the space environment around every planet. The solar wind originates in the corona. The temperature there is so high, millions of degrees, that even the sun's powerful gravity cannot hold onto the plasma. Particles in the corona are moving at such high speeds that they exceed the escape velocity, and they stream outward into space. This isn't a slow leakage, but rather a supersonic flow. The solar wind accelerates rapidly as it moves away from the sun, reaching speeds between 300 and 800 kilometers per second by the time it passes Earth's orbit. The solar wind is mostly protons and electrons, the components of hydrogen atoms, with a small percentage of helium nuclei and trace amounts of heavier ions. It's incredibly tenuous, far less dense than the best vacuum we can create on Earth. At Earth's distance from the sun, there are only about 5 to 10 particles per cubic centimeter in the solar wind. For comparison, the air you're breathing has about 25 quintillion molecules per cubic centimeter. So the solar wind is essentially a vacuum. Embedded in the solar wind is the sun's magnetic field. Because the plasma is electrically charged and the sun is rotating, the magnetic field gets dragged along with the outflowing plasma. The field lines don't extend outward radially but instead form spiral patterns, like water from a rotating lawn sprinkler. This structure, called the Parker spiral, after the physicist who first described it, means that the magnetic field at Earth's orbit is actually pointing partially sideways rather than directly away from the sunday. This combination of charged particles and magnetic field has profound effects throughout the solar system. When the solar wind reaches a planet with a magnetic field, like Earth, it compresses the planet's field on the sunward side and stretches it out into a long tail on the night side. Earth's magnetosphere, the region dominated by our planet's magnetic field, acts as a protective bubble that deflects most of the solar wind around us. Without this protection, the solar wind would steadily strip away Earth's atmosphere, as appears to have happened to Mars, which lost most of its magnetic field early in its history. But the magnetosphere is not a perfect shield. At high latitudes near the poles, magnetic field lines connect directly to the solar wind. Charged particles can follow these field lines down into the upper atmosphere, where they collide with oxygen and nitrogen atoms. These collisions excite the atoms, causing them to emit light, the beautiful, shimmering curtains of the aurora borealis in the north and aurora australis in the south. The colors depend on which atoms are being excited and at what altitude. Oxygen produces green light at lower altitudes and red light at higher altitudes. Nitrogen produces blue and purple hues. Auroras are the most visible manifestation of the sun's magnetic influence on Earth, but they're just one part of a broader phenomenon called space weather. Just as Earth has weather changes in atmospheric conditions, driven by the sun's heating, the space environment also has weather changes driven by the sun's magnetic and energetic output. Space weather becomes particularly intense when the sun releases sudden bursts of energy. Solar flares are explosive releases of energy from the sun's surface, typically associated with sunspot groups where magnetic fields are particularly strong and complex. When magnetic field lines reconnect, releasing stored energy, the plasma in that region can be heated to tens of millions of degrees in a matter of minutes. The flare emits intense radiation across the electromagnetic spectrum, from radio waves to gamma rays. The most powerful flares release as much energy as billions of nuclear bombs. This radiation reaches Earth at the speed of light, arriving just over 8 minutes after the flare occurs. When it hits Earth's upper atmosphere, it can cause sudden ionization, disrupting radio communications and GPS signals. These are called radio blackouts, and they can affect large regions of Earth, particularly on the day side where the sunlight is already ionizing the atmosphere. But solar flares are often accompanied by something even more dramatic: coronal mass ejections, or CMEs. These are huge bubbles of plasma and magnetic field that the sun expels into space. A CME can contain billions of tons of plasma traveling at speeds from a few hundred to several thousand kilometers per second. If a CME is directed toward Earth, it takes anywhere from 18 hours to several days to reach us. When a CME reaches Earth, it can cause a geomagnetic storm. The CME's magnetic field interacts with Earth's magnetosphere, compressing it and injecting energy into the system. This causes the magnetosphere to become disturbed, with intense currents flowing through the magnetosphere and into the upper atmosphere. During severe geomagnetic storms, these currents can be strong enough to induce electrical currents in long conductors on the ground, such as power transmission lines and pipelines. In extreme cases, these currents can damage transformers and cause widespread power outages. The most famous historical example is the Carrington event of September 1859. A massive solar flare and associated CME hit Earth, causing the most intense geomagnetic storm on record. Telegraph systems around the world failed or malfunctioned. Telegraph operators reported receiving electric shocks, and some telegraph equipment continued to send and receive messages even with their power supplies disconnected powered purely by the currents induced by the geomagnetic storm. Auroras were visible as far south as the Caribbean, so bright that people reported being able to read by their light at midnight. If a Carrington-scale event happened today, the consequences would be far more severe because our modern technological society is much more dependent on electrical systems. Satellites could be damaged by the intense radiation. Power grids could be knocked out for weeks or months. Some estimates suggest that a severe geomagnetic storm could cause trillions of dollars in economic damage and take years to fully recover from. More recently, in November 2025, we saw another significant space weather event. A series of powerful X-class solar flares erupted from an active region on the Sun, including an X5. One flare that was the strongest of the year. These flares were accompanied by coronal mass ejections that reached Earth within about 18 hours. The resulting geomagnetic storm reached G4 level on NOAA's 5-point scale, with Earth's magnetic field compressed significantly. Auroras were visible at unusually low latitudes, with sightings reported as far south as Florida. The storm disrupted some satellite operations and caused radio blackouts across Europe, Africa, and Asia. These events remind us that the Sun is not a passive light source, but an active, dynamic star that can affect Earth in tangible ways. Space weather forecasting has become an important field, with agencies like NOAA's Space Weather Prediction Center monitoring the Sun constantly for signs of flares and CMEs. Satellites positioned at the L1 Lagrange point, about 1.5 million kilometers from Earth toward the Sun, provide early warning when a CME is approaching. This gives us anywhere from 15 minutes to an hour to prepare, allowing power grid operators to adjust loads, satellite operators to put spacecraft into safe mode, and airlines to reroute flights away from polar regions where radiation exposure increases during storms. The solar wind and space weather effects extend throughout the solar system. At the outer edge, perhaps 100 astronomical units from the Sun, 100 times Earth's distance, the solar wind finally slows down and mingles with the interstellar medium, the tenuous gas that fills the space between stars. This boundary, called the heliopause, is where the Sun's influence gives way to the larger galactic environment. The Voyager 1 spacecraft crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. It took more than 35 years of travel at escape velocity to get there, giving you some sense of how far the Sun's reach extends. Number. The steady heartbeat. For all its violence and activity, the nuclear explosions in its core, the churning convection, the explosive flares and mass ejections, the Sun has been remarkably stable over billions of years. This stability is what makes life possible. The Sun is currently what astronomers call a main sequence star. This term comes from a diagram called the Hertzsprung-Russell diagram, which plots stars according to their temperature and luminosity. When you plot large numbers of stars on this diagram, most of them fall along a diagonal band called the main sequence. Stars on the main sequence are in their longest and most stable evolutionary phase, steadily fusing hydrogen into helium in their cores. The Sun has been on the main sequence for about 4.6 billion years and will remain there for approximately another 5 billion years. This main sequence lifetime is determined by the star's mass. More massive stars burn their fuel much more quickly and have shorter lifetimes. A star 10 times the mass of the Sun might only last 10 million years on the main sequence. A star half the Sun's mass will burn for tens of billions of years. The Sun, with a mass about 330,000 times that of Earth, has a main sequence lifetime of approximately 10 billion years. We're roughly at the midpoint. During this main sequence phase, the Sun undergoes gradual changes. It's slowly getting brighter and slightly larger as it ages. This happens because as hydrogen is converted to helium in the core, the helium ash builds up. Helium nuclei don't fuse at the temperatures and pressures currently in the core, so they just accumulate. This helium is denser than hydrogen, so the core becomes gradually denser and slightly contracts. The contraction heats the core, which increases the fusion rate slightly, which increases the energy output. The result is a slow, steady increase in luminosity. When the Sun first settled onto the main sequence 4.6 billion years ago, it was about 30% dimmer than it is today. It has been gradually brightening at a rate of about 1% every 100 million years. The early Earth was receiving significantly less solar energy than it does today, which creates an interesting puzzle called the faint young sun paradox. Geological evidence suggests that liquid water existed on Earth's surface as far back as 4 billion years ago. But with the Sun 30% dimmer, Earth should have been frozen. The resolution is that Earth's atmosphere must have contained much more greenhouse gases, probably carbon dioxide and methane, which trapped heat and kept the planet warm despite the fainter Sunday. As the Sun has brightened, Earth has avoided overheating partly because life itself has helped to regulate the atmosphere. Photosynthetic organisms removed much of the carbon dioxide, converting it into oxygen and organic material. Limestone deposits and other processes locked carbon away. The result has been a planet that has remained habitable despite the changing luminosity of its star. This is a remarkable example of planetary evolution and possibly life itself working together to maintain conditions suitable for continued life. The Sun will continue this gradual brightening for the remainder of its main sequence lifetime. In another billion years, it will be about 10% brighter than today. In 5 billion years, when it's nearing the end of its hydrogen-burning phase, it will be about 67% brighter than it is now. These changes will have dramatic effects on Earth, as we'll explore in a moment. For now, let's appreciate what the main sequence represents. It's a phase of equilibrium, a balance between gravity trying to compress the star and fusion energy trying to expand it. This balance has remained stable for billions of years, allowing Earth and the other planets to orbit in predictable paths, allowing life to evolve and diversify, allowing complex ecosystems to develop and persist. The stability of the Sun is something we take for granted, but it's actually quite remarkable. Not all stars are this stable. Variable stars can change their brightness significantly over days, weeks, or months. Some stars are in binary systems where they exchange mass with their companions, leading to dramatic eruptions. Some young stars undergo violent outbursts as they're still settling into equilibrium. We happen to live around a star that found its balance early and has maintained it with only gradual changes for eons. This consistency is one of the great gifts of our cosmic situation. The Sun's stability extends beyond just its luminosity. The orbits of the planets have been stable because the Sun's gravitational pull hasn't changed significantly. The composition of the solar wind has remained fairly consistent. Even the 11-year activity cycle, with its variations in sunspots and flares, represents a regular pattern rather than chaotic behavior. This is the Sun in its prime, in the long Middle Age that lasts for billions of years. It's doing what it was built to do, fusing hydrogen, emitting light, holding the solar system together with its gravity, filling space with its magnetic field and particle wind. It's been doing this longer than Earth has existed as a habitable world, and it will continue doing it for billions of years to come. But eventually, inevitably, things will change. The hydrogen fuel in the core won't last forever, and when it runs out, the Sun will undergo transformations that will reshape the solar system entirely. Number. The slow brightening. Before we look billions of years into the future, we need to understand what will happen much sooner on timescales that are still unimaginably long by human standards, but brief in cosmic terms. The Sun's gradual brightening will eventually make Earth uninhabitable, long before the Sun exhausts its core hydrogen. In about 1 billion years from now, the sun will be approximately 10% brighter than it is today. This might not sound like much, but it will have profound effects on Earth's climate. The increased solar energy will warm the atmosphere and oceans. More water will evaporate from the oceans, increasing the amount of water vapor in the atmosphere. Water vapor is itself a greenhouse gas, trapping heat. This is called a moist greenhouse effect, and it's the beginning of the end for Earth's habitability. As more and more water vapor accumulates in the upper atmosphere, that water will be exposed to intense ultraviolet radiation from the sunday. The hydrogen, being light, will escape into space. The oxygen will either escape as well or react with rocks on the surface. Either way, Earth will be losing its water. Think about what this means for Earth's future. The oceans that have covered most of our planet for 4 billion years will slowly begin to disappear. It won't happen overnight. This is a process that unfolds over hundreds of millions of years. But it's inexorable. The coastal regions will be the first to go as sea levels drop and former ocean beds become exposed dry land. The shallow seas will evaporate, leaving behind salt deposits and ancient sediments. Deeper ocean basins will shrink, becoming saltier and warmer as their volume decreases. Life will have to adapt to these changing conditions, if it can. Marine ecosystems will be compressed into smaller and smaller volumes of water. Species that depend on coastal habitats will need to evolve or migrate or face extinction. On land, the climate will become increasingly hot and dry. Deserts will expand. Forests may give way to grasslands, and grasslands to scrubland, and then to bare rock and sand. Rainfall patterns will shift dramatically as the hydrological cycle is disrupted by the loss of ocean surface area. The process will accelerate. As the atmosphere gets hotter and moister, as more water escapes to space, the conditions will approach what's called a runaway greenhouse effect. The oceans will begin to boil. The atmosphere will become thick with steam. The surface temperature will climb past 100 degrees Celsius, then higher still. Complex life will become impossible. Even the most extreme microorganisms, the extremophiles that can survive in boiling hot springs or deep underground, will eventually be killed by the heat. Some organisms might survive longer than others. Life has shown remarkable resilience on Earth, persisting through ice ages, asteroid impacts, volcanic eruptions, and dramatic shifts in atmospheric composition. There will likely be refugia places where conditions remain marginally tolerable for longer. Deep underground, where the temperature is buffered by kilometers of insulating rock, microbial life might persist. In caves with trapped ice, in deep aquifers, in places where liquid water can still exist, even as the surface becomes uninhabitable, life might cling on. But these refugia will shrink over time. The heat will penetrate deeper. The water will eventually be gone, even from the depths. And when the last pocket of liquid water disappears, the last microbe will die, and Earth will become truly lifeless for the first time in 4 billion years. Different models predict slightly different timelines for these events. Some suggest that the moist greenhouse will begin in about 1 billion years, and that the oceans will be substantially evaporated within 1.5 billion years. Others suggest Earth might hold on to habitability for as long as 2 billion years, particularly if life and geological processes can somehow continue to regulate the atmosphere. But all models agree that the steadily brightening sun will eventually make Earth's surface too hot for life. By about 3 billion years from now, the sun will be about 40% brighter than today. At this point, Earth will likely resemble Venus, a hellish world with a thick carbon dioxide atmosphere, crushing surface pressure, and temperatures hot enough to melt lead. Any remaining water will have been lost to space. The surface will be baked dry. The oceans, which have existed for 4 billion years, will be gone. The ice caps, long since melted, will be just a distant memory recorded in geological strata. Life, if any remains, will be confined to the deep subsurface, far from the scorching surface. This is a sobering thought. Not because humanity will be affected, will either be long extinct or have moved to other worlds billions of years before this happens, but because it illustrates that Earth's time as a habitable world is limited. We exist in a window, a span of time when our planet orbits at just the right distance from a star that's just the right brightness. That window opened when Earth formed and cooled enough to have liquid water on its surface, perhaps 4.2 billion years ago. It will close in about 1 billion years, when the brightening sun makes liquid water impossible. That's a 5 billion year window. It sounds like a long time, and it is, but it's not forever. The same fate awaits every planet orbiting every main sequence star. As stars age and brighten, their habitable zones move outward. A planet that was initially in the habitable zone will eventually become too hot. Conversely, planets that were initially too cold might warm up and become habitable later in their star's life. Some scientists have speculated about future habitability in the outer solar system. As the sun brightens over the next billion years, the habitable zone will shift outward. Currently, the habitable zone extends from about 0.9 to about 1.7 astronomical units, roughly from Venus's orbit to beyond Mars. But billions of years from now, as the sun brightens further, the habitable zone could extend much farther out, potentially reaching the orbits of Jupiter's and Saturn's moons. Moons like Europa and Enceladus, which currently have subsurface oceans beneath thick ice shells, might thaw out. Titan, with its thick nitrogen atmosphere and lakes of liquid methane, might warm up enough for water to be liquid on its surface. These worlds could become habitable, at least temporarily, as the sun brightens. Of course, this would happen over such vast timescales that any life currently on Earth would have long since perished or evolved beyond recognition. But it's fascinating to think that the dying of one habitable world might enable the birth of habitability elsewhere in the same solar system. This slow brightening, this gradual heating of the inner solar system will continue until the sun finally exhausts the hydrogen in its core. And that's when the real drama begins. Number. The red giant transformation. About 5 billion years from now, give or take a few 100 million years depending on exactly how you calculate it, the sun will run out of hydrogen in its core. For 5 billion years, it will have been steadily converting hydrogen into helium, and the helium ash will have been building up in the core. At first, this doesn't cause any immediate problems. The core continues fusing the hydrogen that remains, but eventually, the hydrogen is exhausted. The fusion stops. This is a critical moment in the life of a star. Fusion has been producing the outward pressure that balances gravity's inward pull. With fusion shut down in the core, that balance is broken. Gravity wins. The core, now composed entirely of inert helium, begins to contract under its own weight. As the core contracts, it heats up. This is another consequence of basic physics. Compressing gas heats it. The core, though not fusing anything, gets hotter and hotter as it shrinks. The temperature climbs past 20 million degrees, 30 million, higher still. This heat radiates into the layers just above the core, which still contain hydrogen, and those layers are now hot enough to fuse hydrogen, so fusion hasn't stopped, it's just moved. Instead of happening in the core, hydrogen fusion is now happening in a shell surrounding the inert helium core. This shell is actually more productive than the core was. It's fusing hydrogen into helium at a faster rate, producing more energy than the sun has ever produced before. And this extra energy has to go somewhere. It pushes the outer layers of the sun outward. The sun begins to swell. The photosphere, which has been at a fairly stable radius for billions of years, starts expanding outward. As it expands, it cools, spreading the same amount of energy over a larger surface area. The surface temperature drops from about 6,000 degrees Celsius down toward 3,000 degrees. At this cooler temperature, the sun's color shifts from yellow-white to orange and then to red. The sun is becoming a red giant. The expansion is relatively slow at first, taking place over hundreds of millions of years. But it's relentless. The sun will grow to dozens of times its current diameter, then hundreds of times. The visible disk in Earth's sky, which currently subtends about half a degree, will grow larger. If anyone were still on Earth to witness it, though of course the planet will have been uninhabitable for billions of years, by this point they would see the sun gradually growing in the sky, becoming larger month by month, year by year, century by century. Its color would shift from the familiar yellow to a deep, ominous orange-red. The once distant sun would loom ever larger, filling more and more of the sky. Eventually, about 6 to 7 billion years from now, the sun will reach its maximum size as a red giant about 256 times its current radius. At this size, the sun's surface will extend to roughly 1.2 astronomical units, which is beyond the current orbit of Venus. If you could somehow stand on what's left of Earth and look up, you would see a wall of red plasma filling half the sky, a truly alien and terrifying sight, the dying star that once gave life, now threatening to consume everything in its path. Mercury, the closest planet to the sun, will definitely be consumed. The expanding sun will engulf it, and Mercury will spiral inward through the sun's outer atmosphere, heating up and eventually vaporizing completely. Venus will almost certainly meet the same fate. Its orbit is at 0.7 astronomical units, well inside the red giant sun's radius. Venus will be swallowed and destroyed. Earth's fate is more uncertain. Our planet currently orbits at 1 astronomical unit, right at the edge of the red giant sun's maximum extent. Will we be engulfed or not? The answer isn't straightforward because the situation is more complicated than it first appears. As the sun expands and becomes a red giant, it will also lose mass. The outer layers of a red giant are very loosely bound, and the sun will shed them into space through a powerful stellar wind. Over the red giant phase, the sun will lose approximately 30 to 40% of its total mass, roughly a third of what it has now. This mass loss weakens the sun's gravitational pull on the planets. As a result, the planetary orbits will expand. Earth's orbit might drift outward to perhaps 1.5 astronomical units. So there's a competition. The sun is expanding outward, but Earth's orbit is also moving outward. Which happens faster determines Earth's fate. Most calculations suggest that the orbital migration won't be enough. Even though Earth's orbit will expand, the sun will likely expand faster. However, recent discoveries of Earth-like planets surviving at similar distances around other red giant stars suggest our planet's fate remains genuinely uncertain. The most likely scenario is that Earth will be engulfed by the outer atmosphere of the red giant sun, though it's not entirely certain. What happens to a planet that gets swallowed by its star? The outer layers of a red giant are very diffuse, much less dense than Earth's atmosphere, but they're still much denser than the near vacuum of space. When Earth enters these layers, it will experience drag, like a spacecraft entering an atmosphere. This drag will slow Earth down, causing it to spiral inward. As it spirals inward through progressively denser layers, the drag increases. Earth will heat up from friction, first at its surface and eventually throughout. The oceans, long since boiled away billions of years earlier, won't even be a memory. The atmosphere will have been stripped away. What remains is the rocky, metallic core of a once living world. Eventually, Earth will spiral all the way down into the denser layers of the sun, perhaps even into the region where temperatures reach thousands of degrees. At that point, Earth will break apart, vaporize, and disperse into the solar plasma, the atoms that once made up mountains and oceans, that once formed the bodies of countless living things, will become part of the sun itself. The Earth will die not with a bang, but with a slow dissolution into star stuff. Mars, orbiting at 1.5 astronomical units, will probably survive the red giant phase, though it will be subjected to intense heat and radiation. The gas giants Jupiter, Saturn, Uranus, and Neptune are far enough out that they'll definitely survive, though they may lose some of their outer atmospheric layers to the intense radiation. But even if some planets survive, the solar system will be utterly transformed. The inner solar system will be gone. The habitable zone will have moved far outward, perhaps extending from 49 to 71 astronomical units out into the Kuiper belt, beyond the orbit of Neptune. Some of the icy moons in the outer solar system might briefly thaw and become habitable as they're bathed in the red giant's light. But this will be a short-lived phenomenon, lasting only as long as the red giant phase itself. Number. The final chapters. The sun's time as a red giant will last about 100 to 130 million years. This is short compared to the 10 billion years it will have spent on the main sequence, but it's still a very long time by human standards. During this period, the sun will undergo further changes. Eventually, the helium in the core will reach temperatures and densities high enough for it to start fusing. At about 100 million degrees Celsius, helium nuclei can overcome their mutual repulsion and fuse together. 3 helium nuclei can fuse to form carbon, and carbon can capture another helium nucleus to form oxygen. This helium fusion releases energy, providing a new power source for the star. But the onset of helium fusion doesn't happen smoothly. The core has become so dense that it's in a degenerate state, a quantum mechanical condition where the usual gas laws don't apply. In a degenerate gas, pressure doesn't depend on temperature the way it normally does. So, when helium fusion starts and the temperature rises, the core doesn't expand to regulate the fusion rate like it normally would. Instead, the fusion rate skyrockets. In a matter of minutes, a huge amount of energy is released in what's called a helium flash. The helium flash is a brief, violent event buried deep in the star's core. It doesn't blow the star apart, but it does dump enormous energy into the core, lifting it out of the degenerate state. After the helium flash, the core settles into a more stable state, fusing helium into carbon and oxygen at a controlled rate. This provides energy that supports the star against gravity, and the red giant actually shrinks slightly and becomes somewhat more stable. This helium-burning phase lasts much shorter than the hydrogen-burning main sequence, perhaps just 100 million years. The star is now burning 2 fuels at once, helium in the core and hydrogen in a shell around the core. Eventually, the helium in the core runs out, and we're back to the situation we had before. An inert core, this time made of carbon and oxygen, contracting and heating up, with fusion happening in shells above it. At this point, the sun will enter the final phase of its red giant existence. It will pulsate, swelling, and shrinking in irregular cycles. It will lose mass even more rapidly, with strong stellar winds carrying material into space. Eventually, the sun will have lost all of its outer envelope. What remains is the hot, dense core, a ball of carbon and oxygen about the size of Earth, but containing about 50 to 60% of the sun's original mass. This is a white dwarf, and it's one of the final states of stellar evolution for stars like the Sunday. The material that was blown off into space will form a glowing shell around the white dwarf. Illuminated by the intense ultraviolet light from the hot core, this shell of gas glows with beautiful colors. Reds from hydrogen, blues and greens from oxygen and nitrogen. This is called a planetary nebula, though it has nothing to do with planets. The name comes from early astronomers who thought these fuzzy, round objects looked like planets through their telescopes. Planetary nebulae are among the most beautiful objects in astronomy. Each one is unique, shaped by the specific way the star lost its outer layers and by any binary companions or planets that might still be orbiting. They come in tremendous variety. The Ring Nebula, the Cat's Eye Nebula, the Helix Nebula. These famous objects are all planetary nebulae, the beautiful corpses of sun-like stars. The white dwarf at the center is extraordinarily dense. Packing about half the mass of the sun into a sphere the size of Earth means densities around 1 million times that of water. A teaspoon of white dwarf material would weigh several tons. The atoms in a white dwarf are crushed so close together that electrons are stripped from their nuclei, and the whole star is supported by something called electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed into the same space. White dwarfs are initially very hot, up to 100,000 degrees Celsius or more, because they're the exposed cores of stars. But they have no internal energy source. They're not fusing anything. They're just hot, and they're gradually cooling by radiating their stored heat into space. A white dwarf cools very slowly. Because it's so dense, theoretical calculations suggest it takes trillions of years for a white dwarf to cool to the point where it no longer glows. Eventually, after an almost inconceivably long time, the white dwarf will fade to become a black dwarf, a cold, dark cinder of carbon and oxygen, a relic of a star that once shone brightly. But trillions of years is longer than the current age of the universe. The universe is only about 13.7 billion years old. Even the oldest white dwarfs, formed from the first stars that evolved off the main sequence, haven't had time to cool completely. There are no black dwarfs yet in the entire universe, but there will be, eventually, when the universe is vastly older than it is now. This is the ultimate fate of the sun, a gradual fade from white dwarf to black dwarf over timescales that dwarf even the sun's 10 billion year main sequence lifetime. The sun will persist as a stellar remnant far longer than it will have existed as an active star. And throughout that long fade into darkness, it will drift through the galaxy, no longer the center of a planetary system, no longer the source of life and light, just a dense, cooling ember slowly approaching equilibrium with the near absolute zero temperature of space itself. Number. The changing habitable zone. Let's step back from these distant futures for a moment and consider what they mean for habitability in the solar system. We tend to think of the habitable zone as fixed, but it's not. As a star evolves, its habitable zone moves. Currently, the sun's habitable zone, the region where liquid water can exist on a planet's surface, extends from about 0.9 to about 1.7 astronomical units. Earth sits comfortably in the middle of this zone. Mars is near the outer edge, too cold for liquid water on its surface today, though evidence suggests it had liquid water in the past when its atmosphere was thicker. Venus is near the inner edge, too hot, trapped in a runaway greenhouse effect. As the sun brightens over the next billion years, the habitable zone will move outward. What is now comfortably habitable will become too hot. What is now too cold will warm up and potentially become habitable. This is a gradual process, happening over hundreds of millions of years, but it means that the definition of where life can exist is constantly changing. During the red giant phase, the habitable zone will shift dramatically outward. When the sun expands to many times its current radius, it will be much more luminous than it is now. The habitable zone could extend from about 49 to 71 astronomical units. This is far out in the solar system, in the region we now call the Kuiper Belt, where small icy bodies orbit beyond Neptune. What's out there at those distances? Well, we have Pluto and the other dwarf planets, which are essentially large frozen balls of rock and ice. We have Eris, Makemake, Haumea, and countless smaller bodies. But we also have Neptune itself, and Neptune's moon Triton, and beyond Saturn we have Titan, and around Jupiter we have Europa, Ganymede, and Callisto. While these gas giants won't be in the new habitable zone, their moons might be if the red giant sun's heat reaches far enough out. Imagine Titan, currently a frigid world with a thick nitrogen atmosphere and lakes of liquid methane on its surface, warming up as the sun becomes a red giant. The methane lakes would evaporate. The water ice that makes up much of Titan's crust could melt. For a brief period, brief in cosmic terms, meaning perhaps tens of millions of years, Titan could have liquid water on its surface. Could life begin there? It seems unlikely in such a short time, but the possibility is intriguing. Europa, currently covered in water ice with a vast subsurface ocean, might see its ice shell melt away, exposing that ocean to space. The ocean might freeze on the newly exposed surface, or it might persist if the atmospheric pressure is right. Either way, Europa would be dramatically transformed. These transformations would be short-lived. The red giant phase lasts only about 100 million years. That's long enough for significant changes to occur, but probably not long enough for complex life to evolve from scratch. Still, it's a fascinating thought experiment about how the stages of stellar evolution reshape the environments around them and create new, temporary opportunities for habitability. After the red giant phase, when the sun has become a white dwarf, the habitable zone will shift dramatically inward again. White dwarfs are much fainter than main sequence stars. Our sun as a white dwarf might be only 1% as luminous as it is now. The habitable zone around such a dim object would be very close in, perhaps only a few million kilometers from the white dwarf. Any surviving planets at those distances would be either consumed during the red giant phase or left far outside the new habitable zone. However, there's an interesting twist. Planets could potentially form again around white dwarfs from the material of the planetary nebula or from debris left over from planets that were destroyed. There's even evidence that some white dwarfs have planets orbiting them. We've detected planet-like objects and seen signs of planetary material falling onto white dwarfs. These second-generation planets could potentially be habitable if they formed at the right distance. The universe is old enough now that some white dwarfs have had billions of years to cool and for planets to potentially form around them. Could there be life around white dwarf stars? It's speculative, but not impossible. It would require very different conditions than life on Earth. Close orbits around dim stars, tidal locking, one face always toward the star, unique radiation environments. But life has shown remarkable adaptability on Earth, existing in hot springs, deep oceans, frozen Antarctic ice, and even miles underground. Who's to say it couldn't adapt to the strange environment around a white dwarf? These questions remind us that habitability is not a simple yes or no question. It's a function of many variables: the star's properties, the planet's distance, the planet's atmosphere, the presence of water, the radiation environment, and many others. As stars evolve and conditions change, the possibilities for life shift and transform. The universe is far more dynamic and interesting than we might imagine when we just look at a snapshot of the current state. Number, gratitude, and perspective. Let's return to the here and now, to the present moment in the sun's long life and Earth's fortunate existence. We live in a remarkable time and place, cosmically speaking. The sun is stable, middle-aged, neither too young and variable, nor too old and dying. Earth orbits at just the right distance to have liquid water on its surface. Our atmosphere is transparent to visible light, but opaque to harmful ultraviolet radiation. The sun's magnetic field and Earth's magnetosphere work together to protect us from the worst of the solar wind. This is not guaranteed. We know of many solar systems where the conditions are quite different. Some orbit very close to their stars, heated to scorching temperatures. Some orbit far away, frozen and dark. Some orbit variable stars that flare unpredictably. Some orbit in binary systems where two stars dance around each other, creating chaotic radiation environments. Some planets have no magnetic fields and are slowly losing their atmospheres to space. We live in a moment of balance. Earth has been habitable for about 4 billion years and will remain habitable for roughly another billion years. That's a 5 billion year window. The sun has been stable on the main sequence for 4.6 billion years and will remain there for roughly another 5 billion years. We exist in the middle of these windows. Think about what this means. Every ancestor you've ever had, going back to the first replicating molecules on the early Earth, has lived under this same sunday. The photosynthetic bacteria that first learned to split water molecules and release oxygen, fundamentally transforming Earth's atmosphere. They were powered by this same star. The first animals that crawled out of the oceans onto land, the first plants that colonized the continents, the dinosaurs that dominated for 160 million years, the mammals that inherited the Earth after the dinosaurs' extinction, the primates that evolved increasingly complex brains, the early humans who first looked up at the sun and wondered what it was, all of them, every one, lived under the light of this stable, middle-aged star. The sun has been the constant in the story of life on Earth. Continents have drifted, oceans have opened and closed, ice ages have come and gone, species have evolved and gone extinct, mountains have risen and eroded away. But through all of it, the sun has been there, slightly brighter than it was at the beginning, but otherwise remarkably consistent, pouring energy onto Earth's surface, driving photosynthesis, evaporating water to form clouds, warming the atmosphere to create winds, making weather and climate and all the complex systems that support life. Every calorie of energy in your body came from the sunday. If you ate plants, they captured solar energy directly through photosynthesis. If you ate animals, those animals ate plants, or ate animals that ate plants. The energy chain always leads back to photosynthesis, and photosynthesis requires sunlight. The warmth in your body, the energy that powers your muscles and nervous system and keeps you alive, is solar energy transformed through a chain of chemical reactions, but ultimately sourced from fusion reactions in the sun's core. The atoms in your body came from the sun too. The hydrogen in your water molecules was forged in the Big Bang, but the oxygen was created in stellar fusion. The carbon that forms the backbone of organic molecules, the nitrogen in amino acids and DNA, the calcium in your bones, the iron in your blood, all of these were created in stars. When those stars died, they scattered this enriched material into space. Subsequent generations of stars formed from this enriched gas, and planets formed around them. Earth coalesced from this material about 4.6 billion years ago, and you've been made from it. You are literally made of star stuff. There's a chain of connection from the sun to you that's both physical and metaphorical. The light that warms your skin left the sun's surface 8 minutes and 20 seconds ago, but it was created in the core 170,000 years ago. The energy in your body came from the sun within the last few days or weeks, depending on what you ate. The atoms in your body were created in stars billions of years ago. The planet you stand on formed alongside the sun 4.6 billion years ago. Your existence is woven into the cosmic fabric in ways both intimate and vast. And one day, billions of years from now, the sun will transform into something else. The stable equilibrium that has persisted for eons will break down. The sun will swell, consuming the inner planets, perhaps including Earth. It will shed its outer layers, creating a beautiful nebula. The core will settle into a long fade as a white dwarf, slowly cooling over time spans that exceed the current age of the universe. The story of the sun will continue long after the story of Earth and humanity have ended. But that ending is unimaginably far in the future. For now, right now, the sun shines steadily overhead. It rises each morning and sets each evening. It creates weather, powering the winds and the water cycle. It makes life possible through photosynthesis, providing the energy base for all of Earth's ecosystems. It has done this for longer than mountains have stood, longer than oceans have existed in their current forms, longer than life has been complex and multicellular. The constancy of this cycle is something we rarely stop to consider. But every dawn, every sunset, every season that rolls around again is a testament to the sun's stability. The fact that summer follows winter with such reliability, that the sun rises at predictable times, that we can calculate centuries into the future when eclipses will occur, all of this speaks to the fundamental steadiness of our star. Ancient peoples built monuments aligned with solstices and equinoxes, tracking the sun's annual journey across the sky. They organized their lives, their agriculture, their religious ceremonies around solar cycles, and they could do this because the sun was reliable, because it followed patterns that repeated year after year, generation after generation, millennium after millennium. Take a moment to appreciate that. The next time you feel sunshine on your face, remember that you're experiencing a connection to a star, a vast nuclear furnace 93 million miles away that has been burning steadily for over 4 billion years. The light touching your skin is the end product of a process that began in unimaginable heat and pressure, traveled through layers of star stuff for hundreds of thousands of years, and then crossed empty space to reach you. You are warmed by a star. You are illuminated by fusion. You are connected, physically and fundamentally, to the cosmic processes that have shaped the universe since its beginning. This is the Sunday. This is our star. This is the heartbeat of our solar system, the engine that powers life, the constant presence that has witnessed Earth's entire history and will continue for billions of years to come. We are privileged to exist in this window of stability, to live on a world perfectly positioned in the habitable zone of a perfectly ordinary star that happens to be perfect for life. We are children of the sun in the most literal sense, made possible by its light. And when you look up at the night sky and see other stars, remember that each one of them is a sun too. Each one might have planets. Some of those planets might be inhabitable zones. Some might have life looking up at their own sun, feeling its warmth, depending on its light, wondering about its nature, trying to understand their place in the cosmos. The universe might be full of worlds, orbiting stars, full of life basking in stellar light, full of civilizations studying their own suns and wondering what lies beyond. We are one example among potentially many, but we're the example we know. We're here, now, in this moment of cosmic time, alive beneath our star. That's worth celebrating. That's worth studying and understanding. That's worth protecting and cherishing for as long as we can. Because this combination, this star, this planet, this moment in time is precious and finite. It won't last forever. But it doesn't need to last forever to be meaningful. It just needs to be here now. And it is. If this journey through the sun's past, present, and future has sparked something in you, a sense of wonder, a new appreciation for the star that makes everything possible, a desire to learn more, then I hope you'll stay connected with this community. If you found value in this exploration, a like would truly mean the world. And if you'd like more deep dives into cosmic wonders, consider subscribing. Your support helps me create more of these conversations about the universe we inhabit. The sun will rise tomorrow. as it has for billions of years. You'll feel its warmth, see its light, live beneath its gaze. But perhaps now, you'll understand a little more deeply what you're experiencing. You'll know about the fusion reactions powering that light, the layers it passed through on its journey out, the vast timescales over which the sun has shone and will continue to shine. You'll know that you're witnessing a star in its prime, in the long, stable period that makes life possible. That knowledge doesn't diminish the wonder. If anything, it deepens it. Understanding the sun doesn't make it less beautiful or less important. It makes it more remarkable that such a thing exists at all, creating an island of warmth and light and possibility in the cold darkness of space. We're fortunate to be here, to witness it, to study it, to live by its light. Rest well under the gaze of our star. The sun is out there right now, even if you can't see it on the other side of Earth, if it's nighttime where you are, but still there, still burning, still pouring light and heat into space. It was there before you were born. It will be there after you're gone. It will be there for billions of years to come. That's a comforting thought. In its way, the sun is constant. The sun endures. The sun, our star, the heartbeat of everything we know, shines on.